So our first speaker after lunch is Adnan Hamid from Breaker Verification Systems. He's a well-known CTO and founder of Breaker. He is a noted expert in processor core coherency verification, as well as verification test suite synthesis. Prior to Breaker, Adnan spent several years at AMD in Austin, managing the system logic division, working on complex verification solutions. He holds a BSc from Princeton and an MBA from the University of Texas in Austin. And the title of his talk is RISC-V Certification, applying advanced RISC-V core and SoC verification towards the anticipated certification requirements.
Okay, thank you, Mike. Are you guys still awake after lunch? So, do we need to do anything?
Sorry?
Some chat coming. Do I need to worry about anything coming up on the screen? There was some chat just came through.
Okay, I'll just check.
Fine. So, I'm going to talk to you about two topics that nobody else so far has broached at this conference. The first is RISC-V, and the second is AI. Yeah, and a little bit I wear two hats at this session. One is my role as what I'm doing in RISC-V International and their certification committee, and I'll talk a little bit about that. And the other is as the founder at Breaker and what we're trying to do to address some of those problems from a commercial setting. In my presentation, there are roughly three sections. The first, I'll talk about the need for RISC-V verification and compliance testing and what a big deal it is. And that's really a RBI-oriented conversation. Then I'll talk about what Breaker is doing, how we are solving these problems using AI planning algorithms, which are different than LLMs and machine learning, different branch of AI. And then I'll attach that to how we use that to solve RISC-V verification and show you some of the results that we're generating. So let's start with RISC-V verification and why it's such a huge business headache, right? Can I get this thing to show me the whole slide? Maybe not. Okay. Okay, OpenISA, great. Before this, we all bought our CPUs from ARM, maybe Intel. Those guys have 40 years of experience verifying them, and they have an incredible level of quality. How do we match that when we're trying to do a RISC-V core if we are a brand new design, brand new infrastructure? But much worse, if there are 1,000 people designing RISC-V cores and they don't stay perfectly compatible with one another, that's 1,000 interpretations of the same specification. And you have 1,000 interpretations, you might as well not have the spec. All right. So there's this whole compliance thing that has, so there's a new SIG, Special Interest Group, in RISC-V International called CSC, Compliance Steering Committee. Anyway, and their charter is, hey, if we want RISC-V to proliferate and be good and be all the things we hope for it, we got to have compliance tests for it just as good as the competition, right? And we won't mention who the competition is, but we all know who it is, right? And what does that mean? Here we have profiles that have, I haven't even counted, but over 100 different extensions that they've got to support. Extensions have all kinds of variability in them, right? You can make choices. It is clear that we haven't even got our arms around what the options are, let alone how do we code for which option did you pick and which options need to be verified. But this is a picture, James Ball came up with this picture. See, does that work? Must work, where is it? Oh, there it is, got aim, okay. So it is a worldview that says, okay, somebody who's doing a CPU, they're gonna have to get the CPU certified. How is it going to be certified? TBD. That's going to go into an SoC. That SoC needs its own certification. That will go into some kind of board, and presumably that'll have its own certification, right? So we need solutions at each of these levels, and this is a big, hard problem, okay? And as I've sat through the meetings in RVI, remember, I'm talking with the RVI hat on right now. It is clear that there are a lot of smart people who are really passionate and working really hard, but it's equally clear that collectively, we have no freaking clue what to do about it, okay? It's easy to say, give me a compliance test for add-I, but what's a compliance test for hypervisor look like, right? What's a compliance test for memory ordering look like? Do we know? Do we have solutions? Who knows? And this problem is tiered, right? I mean, as the CPU comes up, you're going to initially want to say, hey, am I at all alive? Can I run a hello world, right? Can I do a single load? Can I do a single store? After that, you're going to push into ISA compliance. Okay, and maybe that comes from RVI. But then you're trying to get into, hey, I built this superscalar 12-ray machine, and I want to test all the corners of the microarchitecture. Is that a compliance problem or not? I don't know, right? But it's a problem that needs to be solved. After that, the full CPU maybe is up, and you're starting to talk about, hey, is the whole CPU good to go from that CPU's perspective, right? Interrupts, memory accesses, operations, all of these things. Then that CPU goes into some kind of SoC. Well, now we've got to worry about, do interrupts work at the system level? Does memory management work correctly when we have multiple CPUs trying to access multiple memory controllers with other uncore our devices? So we need verification for that. Then you start to boot your OSs and start to do your performance and power profiles, right? So there's this tiered thing. And I do think that RVI is thinking more about the lower levels of how do we prove the CPU is good, how do we prove that the SOC CPU went into is good. Or at least that's where we're starting. Okay. And that leads me to this slide, which is a nice segue of taking me from my RVI hat to my Brecker hat, okay? Which is, there are different problems in different domains, right? If you're worried about verifying a single CPU, there's one class of problems that we are really very, very focused on. And that table will show up a little bit later in my presentation, so I won't read through it right now. When that CPU goes into an SoC, then there's a completely new set of problems to worry about at the system level integrity. And as Brecker, why do we think we have something to say about this? Well, we've been in the business of ARM SoC verification for about a decade now, right? As ARM went from their V7 to the V8 architectures, the 64-bit architectures, coherency suddenly became a SoC level problem. None of our customers could spell coherency, and we started with a coherency solution that grew up into being a full SoC validation platform. And now we're pushing that technology down into the core verification. Okay. So now moving on to the second section of my presentation, which is talking a little bit about what Brecker is doing. So take off my RVI hat, right? I got to be careful over here. Put on my CTO hat. We approached the generation of test content as a synthesis problem. So just as you're used to the idea that we write RTL Verilog and you can synthesize gates, and if you want to go from 20 nanometer to 15 nanometer, you resynthesize, the gates are completely different, but they have the same intention. We started playing the same idea for test content generation, right? Single source of truth, and from it, you can have some model, and I'm going to spend a lot of my time talking about how those models are architected. You can constrain it. The tool really wants to generate self-checking test cases, and I'll talk about the strategy we're using and why it wants to generate self-checking test cases. And it spits out not only the stimulus, but the checks, some idea of stimulus coverage, which I'll try to chat a little bit about, and some idea of debug, right? Think GCC for verification. It is saving away some information about the intention of the test so that when things go wrong, it can tell you what the heck it was trying to do. And then that comes through our synthesis flow. And you want to go to a UVM IP bench? No problem. You want to go to a full chip emulation of post-silicon test bench? No problem. So we talk about the idea of vertical reuse, IP to subsystem to full chip, and we talk about the idea of horizontal reuse, simulation, emulation, FPGA, post-silicon. This is the idea behind synthesis. Okay. I promised something about AI. Who here's heard AI recently? Yeah, everybody. Okay. The conversations today are all about deep learning, LLMs, and so on, and this is AI has become synonymous with this. Turns out that, as Mike said, I did my undergrad at Princeton, but was on a scholarship and needed money for books and clothes. I ended up working for a professor in a psych department, and ended up with studying at the feet of the professors who originally came up with neural networks, with rule-based systems, with natural language parsing, right? At the time, there was this idea that there were 3 or 4 different branches of AI that needed studying, solving different problems. And the prof I was working with was working on what at the time was called rule-based systems, today is called planning algorithms. All the learning stuff, love it, don't have anything bad to say about it. But its idea is, hey, I'm going to read in a whole bunch of data and make a guess at what you need. And we have this problem with precision, which we see how well that works with verification. The idea behind planning algorithms is expert systems. Okay, you have human beings go code up for a tool. Hey, here are all the different paths you can go down to try to come up and do something. And you combine that idea with, at various points in the rule base, you can make randomized decisions on whether to go left or right, and you start to create what I think of as a very succinct algebra for describing very complicated verification problems. And we pioneered this some 20 years ago, and since then, there's the Accelera PSS language that's come along that's trying to do some of this. We've been doing this in C++. Doesn't matter, right? Language doesn't matter. It's this idea of being able to take big, complicated verification problems and break them down into smaller pieces. And in the end, if you walk away from this presentation, my one takeaway for you is, okay, Adnan got up there and talked about how we can take really big verification problems and break them down into smaller and smaller pieces so that we as human beings who are very, very bright, but have really small brains in relation to the computers we built, that we can think about one piece of the puzzle at a time. And that's really what I'm here to talk about. So this is a slide that we use to sort of explain the difference between planning algorithms and constrained random generation, right? Constrained random generation is the way we do almost everything in verification today. We talk about test cases, but by and large, we think in terms of generating test cases, right? I mean, okay, constrained random is great, right? If your problem is broad and shallow, you throw a bunch of random traffic at it, and you're gonna get a bunch of coverage, right? One can come along with and say, hey, I'm going to do a constrained random instruction generator, and it just isn't that hard, especially for RISC-V, because the instructions are so nicely orthogonal. Okay. Will that hit all the corner cases of your out of order 8-way pipeline, 12-way pipeline, right? Probably not. You need more intentionality behind those scenarios. You need more patterns. The idea behind these planning algorithms is start with an objective, a scenario you're trying to test. Start with a check. The tool is starting with, I want to check that this outcome works the way I think it does. And then work backwards through this rule set, which is graph-based model, which is derived from the PSS model, compiled from the PSS model. But the point is, I have picked a check, and now let me go solve for a scenario that satisfies my check. Okay. Start with a check, work backwards to construct a scenario that satisfies my check. And this is how the tool creates test cases. A bunch of you are already thinking in your mind, wait a minute, doesn't that look a little bit like formal? Absolutely, right? We're using formal techniques to generate dynamic tests. So this tool never reads your RTL. It can't infer your content from the RTL. And if it could, if a test ever failed, the tool would be broken, right? If you infer your test cases from your actual RTL, and you have a failing test, your inference engine is broken. Okay. So yes, we're using formal techniques to generate test cases. And then this last point is if I can keep track of which paths through this model have been exercised, I can give you a very interesting metric of stimulus coverage that is to be used in conjunction with your existing implementation coverage from, RTL code coverage, functional coverage, and so on. I'm not saying we throw any of that away. What I am saying is you all know that even if you're looking at 100% code coverage, 100% functional coverage on the design, it is extremely hard to infer from that you've exercised all the use cases for your design. And this is about enumerating those use cases and thinking about all those use cases. Okay, so this is an eye chart. Can you guys read this? This is on a slide. I'm trying to now take an abstract idea of begin with end in mind, right? Begin with a check and generate test cases and trying to show how it might be applied to generating RISC-V core verification tests, right? Instruction level tests. I'll give you another picture later on how we think about the SoC level tests. Okay. And I have some big graph over here, right? I am not doing good with my pointer. Anyway, just don't worry about it. Though I do want the pointer. I think I just can't aim my kids. I don't think it's me. I don't think it's a tool issue. Okay. I think it's a user issue. Okay. So the tool start says, okay, my objective is to generate some kind of a C program that I'm going to compile and run in the core. Fair enough. So how does this planning algorithm go about doing it? All these blue boxes represent different modules in the rule set in the graph. And think that under each of these boxes, there's a graph of its own, which in turn might have modules that have graphs of their own and whatnot. So one way to think about this is, okay, let me pick the next privilege level I want to go to. Then let me come up with a nest of branches, right? Just a rat's nest of branches, forward, backwards, loops within loops, set up to do interrupts while you're doing these loops, like everything you can do to confuse the pipeline, okay? And reduce the problem to confusing the pipeline. That's what that branch prediction box worries about, right? How can I create, and right there, he has a huge dictionary of different patterns on what will confuse a pipeline, right? Really tight branches, really long branches, branches that all depend on the same register, branches that depend on different registers, right? So all of these things. But you can put a lot of thought into that little problem. Then you end up with this big mess of branches and you have all these legs, right? So think of a if then else, right? There's the if leg and the else leg of code. So those are all chunks of code that we can fill in. One path you can go down is say, let me just do the compute instructions, right? I'm going to give up on some. But I don't have a mouse either. Yeah, okay, up at the top. The register instructions. I can pick some register instructions. Fine, we know what all our IC instructions are. But then maybe I can put a little bit of thought about how do I pick what registers to use for that instruction, right? Maybe I can come up with things that say, hey, I want to use a small number of registers over and over again, create a whole bunch of read-write hazards on those registers. Or maybe in other cases, I want to make sure that I never repeat a register so that everybody's getting different registers. There'll be no hazards. Pipeline will get different kind of headache over there. Maybe I'm just going to pick one register and do a stream of instructions where everybody's working on the same register and pipeline is really upset with us, right? So all these things. And then at some point, you got to initialize those registers with some well-known value and put a little bit of thought about what are interesting values that can go in. Verification is put in a random number. Random number is good, but put in numbers that are really large, really small. Think about really large 64-bit, really large 32-bit, really large 16-bit. These all hit different corner cases of different instructions, right? So we put a bunch of work in there. And of course, because at each stage, this is coming off the planning algorithm, each time he generates a register instruction, it is natural for him to predict. Therefore, now I think register, X5 should now have this value because I know what instruction I just did and what arguments came into it. So it's always doing self-checking tests. Same thing on the load store side, right? I always say 80% of every CPU is load store, and don't think many people here will argue with me, right? And coming up with good load store instructions, which is actually what Viva's presentation was all about as well, is what we're doing over here, right? Which is, okay, you got your load store instructions. I don't know, there are half a dozen, there are a dozen of them, so that's not hard to come up with. But then picking interesting addresses, right? Which might be your false sharing in a cache line. You might be doing picking addresses that hit the same index in a cache. You might be doing certain stride patterns because some fetchers are trying to predict stride patterns, and you can come up with a pile of different address patterns. Okay, then and those are physical addresses. Then map that through. I'm trying to get to this physical address, but I'm going to map it through the MMU, right? So really what the tool does is says, I'm trying to get to this physical address, so let me build the right MMU pages that'll let me get there through some crazy MMU method. And of course, you add to that hypervisor in the two-stage paging. At this point, my tool is smarter than me, right? I mean, it generates all these crazy things, and it takes me hours to figure out why that's right. Because usually my customer says I'm wrong, right? So, okay. And then that in turn gives you your access, your memory protection hazards, until finally you're doing the memory access. So what's all this? What am I really trying to put in your head, right? The details don't matter. That you can take an outcome-based approach to verification and say, end goal, generate a hard test. First breakdown, let's think about branches. Okay, branches have legs, and in each branch, let's think about what we can do. And we can do compute instructions, we can do load store instructions, and each of those we can successfully decompose. And when you do all of this and flatten into one big graph, which is a little bit what we're showing down over here, you end up with a stupidly large number of possible paths, right? I mean, think, 10 to the 50, right? So very, very large search spaces that you can quickly infer. Again, tying back to Viva's presentation, you think about all the different cross products of how you pick addresses, what instructions, how you do your register hazards. Very quickly, you're multiplying out to a large number of possibilities. And this also brings us to sort of this idea of sequential coverage, right? I talked to you about coverage in the previous slide, that if you can show that you've covered a satisfactory number of those paths, then maybe you have some sense of your stimulus coverage in addition to all the other coverage you're using. And note my language, you've covered some satisfactory set of paths. It turns out the number of paths are much greater than we could ever run in the lifetime of a project. So we're in the business of saying, okay, this is a subset that we deem good enough. Okay, so that's just instruction generation. There is one more layer to all of this, which is scheduling. So you can imagine that this graph walk and it's coming up with clever scenarios. And let's say there's only one thread in the system. And I have a little picture over here now. I'm prefetching what I'm going to talk about at the SOC verification level, right? Anybody who's designing a CPU is going to go into an SOC, so you're thinking about both problems. 5 minutes already? Okay, no problem. Okay. So I have a little CPU subsystem over here for a camera, right? An input device, a camera, an output device, a display, a storage device, and some kind of compute device for photos. If we have one thread, the tool can come along and generate one scenario, generate another scenario. If you have multiple threads, we can generate a scenario, interleave, 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 and all of a sudden you have many cores doing all kinds of different interesting things to create these test cases, right? And you're getting a lot of stress in the system. So this is how we think about the SOC verification. And that's the same place that we do our memory scheduling, right? We both talk about, hey, you got to pick your range of addresses carefully because you want lots of locality of access. We solve the same problem slightly differently, right? We give the tool a bunch of different memory regions to play with, and he has his memory scheduling algorithm that's really greedy about reusing memory, and this is how we create a lot of conflicts. And when we go do all of this, it's being super effective, right? You can, if you look at the kind of traffic you get on fabrics, it's stupid high traffic. We are dropping all kinds of bugs and all kinds of designs. Here we talk about some right? Largely things that we found in open source designs, but very, very effective way of finding problems. Okay. So let's talk a little bit about what we are doing in CPU verification, and then I'll kind of wrap it up. The CPU verification. If I were to come to anybody who's doing a RISC-V core and said, hey, you know, your test plan roughly is going to look like this. You need random instructions. Of course you do, right? But then you need to worry about things like register hazards. Then you got to worry about load store and all the variations that can go on over there. Then you got to worry about conditionals and branches. Some branch prediction is a thing. Exceptions are asynchronous branches, so they're very related, but you got to bring them in. Sorry, exceptions are synchronous. Asynchronous interrupts, you got to bring them in. Then you got to worry about the privilege levels, the MMU, and so on, right? There's a cascade of things, and all of these things are being solved by that big graph I showed you on the first slide. So run through some results, right? So random instructions, though they are carefully in the pattern of registers over there, the registers are not random, right? They're picked to get all kinds of different access patterns, least recently used, most recently used, all of these kinds of things, right? So that's the instructions. Coverage, all right? So here's a quick screenshot of what it looks like to look at coverage, where, I don't know, in this case, apparently we had 103 reachable paths, but only 27 of them have been covered so far, right? So it's a nice way to think about what has and has not been covered, okay? And the planning algorithm, we have a perennial problem in verification. We want stimulus, we want coverage models, and we have no way to be certain that every bucket in our coverage model is satisfiable. So when something's not hit, human beings have to go figure it out whether it was reasonable or not. The graph-based models lend themselves to reachability analysis, so the tool can say, hey, those white nodes I can't get to anyways. Yep. So this is giving you an example of what code looks like for load store. Again, load and store instructions are easy. Coming up with the right addresses, right address patterns is what's interesting. This is showing that we can do exceptions. And this is showing that we can set up really complicated paging scenarios, MMU scenarios, especially the hypervisor stuff has been driving everybody nuts because everybody has a completely different opinion of how it should work. And we have fun debugging things. Okay. And I'll finish up on, and we can do this for multiple cores. So I'm going to stop over there. I had some more material on SOC, but apparently I burnt through my time, and I give it back to Mike.
Okay, thank you very much, Andy.